Now what do we do? What is next? Exactly, getting there, right? So we have now told you how to evaluate a policy. Now the trick comes in, now how to improve the policy, right? How to solve the MDP basically, right? I mean, so this is called evaluation. So this is called control sometimes, right? How do I learn to control the MDP? So this is kind of terminology inherited from so legacy terminology. So this is inherited from control theory. So now I want to know control. So I have evaluation and I have control, right? So I have evaluation, I have done that. So how do I do control? Very simple, right? So I evaluate, fix a policy pi, evaluate, I do generalized policy iteration. So not the extreme form of that. So I just basically do generalized policy iteration. So I fix a policy pi, evaluate it using these kinds of trajectories. I don't run it till convergence, right? So I just evaluate it on few trajectories, right? What do I mean by evaluation on a few trajectories here? I start from some state S, just keep running the trajectory multiple times and then take the average and use that as the value for state S, right? So I have no guarantees that this value that I have computed is a true value for state S under the policy pi. Okay, it's some approximation of that, but I'm happy, I'll stop there, right? So yeah, this is one thing about generalized policy iteration I didn't mention, right? So you don't have to evaluate, you don't have to find the true value of a state also. As long as you can find an approximate value for the state, right, you can just keep going and do your generalized policy iteration. That's essentially what we will do here. So we take a state, we take some samples from those states, right, and then find the value, and then you can go and try to be greedy with respect to that value function. Okay. So any problems that you see here? How will you be greedy with respect to value function? That way. What's the problem being greedy that way? Huh? I need the P, I need the expected RSA. I just told you we are doing Monte Carlo methods because we don't have any of those or we don't need any of those and I can work with a sample model, right? But now you are telling me, oh, you just use that expression to be greedy. I can't. So how do I get around that? You already know how to do it. Huh? I'm going to throw a chalk at you. You of all people know the answer. Don't use the V function, use the Q function. Use the Q value function, right? Do you remember I told you that when you want to recover a policy from the Q, all you need to be is just look at the values of those actions at the state. I don't need to look ahead. Correct? So when I do control, I use the Q function. Okay. Now things get really interesting. So how will I do Monte Carlo evaluation for the Q function? Exactly. So basically I start with an S, fix an A, right, and then follow pi thereafter, then sum up the rewards, whatever the summation, and that gives me one sample for SA, right? That's straightforward enough. And then I do this again, another trajectory, and that. So the crucial thing is I start from S and I take A. Okay. Suppose I reach S again. What do I do? Okay, forget even let me not even go there. Okay, that's an even more fundamental question than that. Okay, so I did S, I did A, I get S1 here. Okay, I did some A1. Right, that's an action that's suggested by policy pi. Right. So this is equal to, right, so pi of S1 is A1, so I do A1, right. Now can I consider this as a sample taken from S1 A1? You would think so. It turns out that if you do this, you get into all kinds of problems, mainly because you would draw a disproportionately larger number of samples from actions corresponding to pi, as opposed to actions that are not corresponding to pi. So it turns out it sets up some conditions in which convergence cannot be guaranteed, right? So you will get some weird answers. So you only have to know. I want to evaluate all SA pairs, right? Only then I can do a policy improvement, right? If I only evaluate the actions corresponding to pi, then I can't do policy improvement, right? So it turns out that I will be disproportionately evaluating actions corresponding to pi, right? And therefore we never do this, right? This whole sample, right, I use it only for updating the value of QSA, right? All these samples I will use only for QSA. I will never use it for QS1A1. For if I want to update the value of QS1A1, I need to start from S1 do A1 and then follow pi thereafter. Right? Huh? That's what I'm saying. You are drawing disproportionately large number of samples about one thing, right? It turns out it sets up some kind of instability in the convergence. Okay, it's a little tricky, and in fact, for a long time, the convergence was an open question for updating on S1A1 also, right? In fact, if you look at the older version of the textbook, they actually say in the textbook it is still an open question, because the textbook was written in 97 and it was proven only in 2002 that it will not converge if you do that, and they had to actually work on it for 2 decades to get to the answer. It's a little tricky to give you the intuition, but the intuition is that, so you are getting too many samples of one thing, therefore the rate of convergence for just that SA is much faster than S1A1 will be much faster than the other kinds of things, and therefore you get all kinds of problems. So one provably convergent way is to only to use the first state and first action.
But then this will take even longer than.
Even longer than what?
Just estimating the value. Even that is.
Yeah, I mean I can estimate the value, but what will I do with it, right? I mean I can estimate only pi, right? I can't do the policy improvement on that. Okay. Having said all of this, it is only for convergence issues, right? It turns out most cases in practice, if you update for S1A1 also it works. Okay. In practice it works, but you can't guarantee convergence. So for guaranteeing convergence, you should do it only on the initial state. So now once I say that you have to do it only on the initial state, your exploring starts becomes even more important. And because you have to start at every state, every action, you have to do that often, right? So that you can get a good estimate for that. And so you can't be greedy at a particular state unless you have taken at least a good fraction of the actions from the state, right, and try to estimate the thing. So now it becomes important. Okay. So one way of avoiding exploring starts, right? Again, it's not clear whether this kind of an approach is going to be convergent. Is to use something called a epsilon soft policy, right? So whenever I say do a policy improvement, I don't give you the greedy policy, I give you a policy that is mostly greedy, right? So most of the probability will go to one action and some of the probability will get distributed to all the other actions. Okay, so that when I start from anywhere and run a trajectory, there is a probability of me sampling all the actions from all the states. It's not just the pi action corresponding to pi, but I can sample all the actions from all the states. So these are called epsilon soft policies. Right, so epsilon soft, it means that every action has at least a probability of epsilon being taken from every state, right? So a uniformly random policy is an epsilon soft policy, right? An epsilon greedy execution of a policy is also epsilon soft policy, right? I mean, where the epsilon is an epsilon by n soft policy. Right? An epsilon greedy policy is an epsilon by n soft policy, right? A purely random policy would be for some epsilon, it's a 1 by n soft policy, right? If I have n actions, it's a 1 by n soft policy. Yeah.
When I am averaging the value state of a state. I mean,
State action
a
pair.
state. So, can I say how much close it will be to the true value? Can I guarantee anything?
Yes. This is a very simple, straightforward thing, right? It depends on the number of samples you draw, right? So there are rates of convergence that you can establish based on the number of samples.
They use this probability concentration like that. They use concentration inequalities.
If you knew the transition probabilities and other things, you could apply concentration inequalities there. Yeah, could. I don't recall the actual results, but you could apply concentration inequalities. Yeah, it's fairly same. I mean, it's more like a textbook exercise application of concentration inequalities, but a little complicated because the distribution you are sampling from is this horrendous distribution that rolls in your. In this case it will be fine, right? It's just a Markov chain. I fixed a pi, right? I have fixed a pi, so there is no question of picking actions here, right? So it just becomes a Markov chain, and essentially I can doing this value computation on the Markov chain. It's very easy to show convergence and rates of convergence. All of those things you can do. And here it becomes tricky because I keep changing the policy from one step to the other, so it becomes a little tricky to show convergence. Right. So epsilon soft policy. So now the question becomes that, hey, we showed you policy iteration converges, right? But that is assuming that you are greedy with respect to the previous policy's value function. Now I am saying don't be greedy, be epsilon soft with respect to the previous value, right? Will this converge? And if so, to what? Okay, we are running out of time, so it will converge, and it converges to an optimal epsilon soft policy where the highest probability will be given to the optimal action. Right. Provided you have a very specific way of generating the epsilon soft policy from the previous iteration. Right. So essentially you take the greedy policy, okay, make it epsilon greedy, or whatever, epsilon by n greedy or something, n epsilon greedy, and then keep doing this. So you will converge to something that is optimal in the sense the highest probability will be on the optimal action. Okay, that's a very simple proof given in the textbook. I encourage you to look at it. Just so you know that this. Okay. Anything else? So any questions on this? So there is one other topic that I have to cover under Monte Carlo methods, which is to do with something called importance sampling. This goes back to one of the questions raised earlier about doing epsilon greedy exploration and so on and so forth. So if I am using an epsilon soft policy, right, for non-exploring starts, right, I'm not really getting what I want, right? I'm actually solving for something else, right? And if you want to evaluate a deterministic policy, right, we saw that you needed to do exploring starts. Right? If you want to evaluate a deterministic policy, you certainly have to do exploring starts. Right? I can't do my usual exploration of the entire state space and then estimate the value of the policy pi. So why? Because it will no longer be the policy pi. Right? So ideally, what I want is a situation where I can behave however I want in the state space, but should give you the value for any policy that you ask me. Is that possible? Can I decouple the policy that I am evaluating from the policy that I am using for behaving? Right? So such kinds of methods are called off policy methods. So whatever we have talked about so far are called on policy methods. Why? Because the samples were generated by the policy which I am trying to evaluate. Right? Whether it's here or here, right? In both cases, when the samples are being generated, it's with respect to the policy that I am trying to evaluate. Right? In off policy methods, the sample will be generated by a different policy, but I will try to evaluate a different policy. technically have 10 more minutes. Okay, let me try and do the simple thing, right? So essentially, what I'm looking at is I want to compute the expectation of some function f of x, where x is sample from some distribution p. Right, this is the notation for that. Some f of x is there, and x is some random variable, right? And x is sampled from some distribution p. So this is the expectation that I want to compute. Okay. Let's keep it simple. So let us assume it's a discrete distribution. So essentially a sum over x, right? Right. So this is the expectation. Now suppose I don't have access to p, okay, but I have some way of sampling x. That is exactly what is the distribution we have, whatever we are, the setup that we have here, right? So then what will I do? So I'll use p and ask you to give me an x, and you'll say 3, then you'll say 4, you'll say 3, 4, 8, 3, 9. You'll just keep telling me numbers like this. Now what I'll do is I'll plug in 3, 4, 8, 9, whatever, I'll plug that into f of x. I'll add up all the values of f of x, divide by n, and I'll give you a number. Right. So how I approximate this is essentially right, where each xi was sampled from p. Right. This is how I do this. Right. But now let us say that I know something about the probability of certain outcomes, okay, but you can only tell me things according to q, let's say. So you are going to give me numbers according to q. So q is a different coin that you are tossing, right? So instead of telling me 3, 3, 8 or something like that, now you are going to tell me 8, 8, 9, 7, 3, 8, 7, 4 or something like that. So 3 and 4 occurred a lot of times in the first sequence of numbers I gave you, but 3 and 4 occur very few times now, but 8 and 9 occur more, right? So now what I do is I am saying that, hey, I don't have p, but I have some other distribution how do I do this? Okay, so I have some other function q, right? So I am going to do this. Okay, is it fine? The people are okay with that? So I am going to rewrite this as right. So I have taken the expectation of f of x with respect to p, right, and I have written it as the expectation of some quantity with respect to the distribution q. So what is this quantity? It is f of x, but weighted by the ratio of the probabilities. Right. So f of x weighted by the ratio of the probabilities. So suppose I want to approximate this. So what will I do? I will do this. So for every sample you give me, I will compute f of x, right, and also multiplied by this ratio of p by q, and then I will add up everything and take the average. That will give me the average of f of x if the samples were drawn according to p. Right. So is that fine? So everybody is with me, right? This equivalence you are all agreeing. So this quantity is called the importance factor. Okay, it tells you how important is a specific x in determining the expectation of f of x with respect to p when I am drawing samples according to q. So it gives me the relative difference in their probability. So if p is very large and q is small, then the importance will be very, very large for that x. So if p of x is very small and q of x is very large, then the importance will be small. I don't care, right, because I am only interested in p of x. Right, if there are comparable probabilities, then I will just use it as it is. Right, p of x by q of x will be 1, I will be using it as it is, so it is fine. Right. So if x happens to be more frequent under q, then I want to give it a lower weight when I compute the expectation. If x happens to be less frequent under q than under p, I want to give it more weight when I am computing the expectation. So this is why it is called importance weighting and or importance weight, I am sorry, importance factor or importance weight. Right. And this whole way of sampling to determine the expectations is called, any guesses? Importance sampling. Yeah.
P of x by q of xi, p of xi by q of xi is already known.
Yeah, I am assuming p and q are known. It is just that you are not able to sample from p. You are not able to draw samples from p. It is easier to draw samples from q. Can you think of a situation where that might happen? When I want to draw samples from a distribution, I told you that I have to find the CDF. So for CDF is not, yeah. Or the CDF is hard to compute, right, for P. So the Q CDF might be easier to compute. So it might be easier to actually simulate samples from Q than from P, right. So in such cases, I might want to do this importance sampling, right. Or in the cases where we are talking about, I have a deterministic policy or I have a policy that is hard for me to execute. I have some random behavior policy, right. So I use that random behavior policy and generate trajectories. So my f of x will become my GT, right, the random sample I draw for the return I take from the trajectory, right, and my P and Q will be policies according to which I am behaving. Okay, good. So is there any condition that we have to be careful about here? Qx shouldn't become 0, right? I mean, if Qx becomes 0, then it's going to become undefined. So one easy way to assume is that the Qx is not 0 for any x, but that's too strong a condition. What we need to assume is Qx is non-zero for any x for which Px is non-zero. So for 0 by 0, you can kind of fudge and say that okay, it doesn't matter, but if Px is non-zero, then Qx has to be non-zero. Right. One easy way to ensure that Qx is non-zero for any Px is epsilon soft. Okay. What?
Exponential weighting like the softmax.
Yeah, so whatever, yeah, epsilon soft. Softmax is another way of generating an epsilon soft policy. Yeah. Right. So however you generate it, which could be epsilon greedy, epsilon soft, whatever, this saying they should ensure that every action has at least some small epsilon probability of being picked. So that way, for whatever be the policy that you want to estimate the value for, this will never become 0 whenever you want, right. So that's a good thing. So this is all fine, right. So one small aside, it turns out that this can suffer from instabilities if you are trying to do this numerically. You are trying to do this. Why is that? Because for cases where Px is non-zero but Qx is close to 0, the importance weights can become very large. Rare events under Qx, right, which are not rare under Px, right, the importance can become very large, disproportionately large, and so you can cause severe oscillations in your estimations. Right, if you add one sample like that. So what people typically do is, instead of doing this, right, instead of dividing by 1 by n, they do so if the ratio Pi by Qi becomes very large, it will happen in the numerator and in the denominator. So it kind of, the ratio will be kept reasonable, it won't oscillate too much. Okay. So this is called normalized importance sampling. Okay, so this is, please don't read anything into equalize. Okay. Okay, so this is also an estimate of this, but this turns out to have slightly higher bias than that, while that will have higher variance. So for every sample that you draw, it can fluctuate tremendously, right? Here, which will not fluctuate as much for every sample, and in the limit both converge to the same answer. So we are all happy, right? But so this this normalized importance sampling is considered better in practice because it's a lot more stable. Okay. So that's it with importance sampling. So I'm going to stop today. So keep the importance sampling in your mind somewhere, right? When you come to class on Wednesday, I'll tell you how to use importance sampling to do off policy learning. Okay, we'll work out exactly what is that P and what is that Q that we have to use for importance sampling. Okay, that will take me about 15 minutes, and after that we'll move to chapter 6. That will be the end of chapter 5. So we have done most of chapter 5 today. So there will be a small bit of chapter 5 left in the next class, and after that we'll move to chapter 6.